Today I want to look at the derivatives of other basic trigonometric functions. And by other, I mean besides sine x and cos x. Sine x and cos x, taking the derivatives of those two functions, can be easy or hard depending on how rigorous you want the proof to be. It can be very easy to talk about what the derivative of sine x and cos x might be, whether the derivative of sine x is cos x and the derivative of cos x is negative sine of x. So I'm going to write those down here on this list here. D by dx of sine x is cos x, and d by dx of cos x is negative sine x. But to actually prove those derivatives rigorously, it takes some pretty good constructions and a study of a couple of pretty intense limits. And so we're going to take those as given, that we've done the easy version of those proofs of sine and cos, and we have those available to us. What's really nice about trig is what happens next is if you have these two derivatives, the derivative of sine and the derivative of cos, then these next four come pretty easily. And so I wanted to show you those in this video. And they're given, all four derivatives are given here. The results are already there, but I want to show you where they come from. So if you had, say, tan of x and you wanted to find its derivative, no really good way to do that except by using a trig identity that tan is sine over cos. And once you have it as sine over cos, then life gets pretty straightforward because you're just going to use, in this case, the quotient rule and the derivatives we already know, which is derivative of sine and cos. So we want to take the derivative of tan. We go derivative of the top. The derivative of sine is cos times the bottom. Minus derivative of the bottom. The derivative of cos is negative sine times the top, which is sine x, all over the bottom squared. And so what I get on the top when I do some simplification is cos squared x plus sine squared x, which is 1 in the numerator there, and I get 1 over cos squared x, which is a perfectly legitimate way to write the derivative. But oftentimes what we do is we convert that to 1 over cos x squared, which is secant squared, which is just a little bit simpler than the previous version of that. So that's usually the way you see it written, is y prime is secant squared x. You see, using only quotient rule and those two derivatives we already had, we can get the derivative of tan. So that's the first one on the list there. The next one I'm going to do, I'll go over here, is I'm going to do the derivative of, I'm going to jump ahead to cosecant of x just because of the way it plays out. So I'm going to go after this one here. So y equals cosecant x, which no good way to find that derivative, but cosecant is 1 over sine of x. And so I could do this as a quotient rule. You might be thinking, oh, well, wouldn't this be easy? Couldn't I do this another way? And I'm going to show that other way in a minute in a different one. But you could go ahead and just use quotient rule. That is, derivative of the top is 0 times the bottom, minus derivative of the bottom, cos x, times the top, all over the bottom squared. And when you see that 0 pop up in the quotient rule, usually that's an indicator that maybe there was a simpler way to do this. I won't say easier, because easier really depends on you, but there might be a simpler way to handle this. And so y prime is negative cos x over sine squared x, which is a legitimate answer, but that's not how you usually see it written, because I can divide this thing up. I can put the negative out front and make a 1 over sine x and a cos over sine x. And so y prime is, well, negative 1 over sine x is cosecant x, and cos over sine is cotan x. And, oh, I forgot the negative up front. Negative cosecant cotan. See, that's a slightly nicer version of that derivative there. All right, so that's 2 of them that I've done already. How much space do I have there? Do I have enough room for another one? I think I do have enough room for another one. If I choose the smaller of the 2, I'm going to choose secant x and just do this a slightly different way, a way that it might have occurred to you while I was doing cosecant x. So secant x is 1 over cos x, and maybe instead of using quotient rule, I could write that as cos x with a negative 1 out front, and then done it as a chain rule. So y prime is negative cosine of x to the negative 2. and then derivative of the inside is negative sine x. And the reason we don't always do it with the chain rule like that, you could do it with the quotient rule like I did up there, is you can do this proof before you even know what chain rule is. You can just do it with quotient rule, whereas this requires just a little bit more knowledge, and nothing too crazy there. And then so the negatives in this case cancel, and so what I get is sine x over cos squared x, which I'm going to write as 1 over cos times sine over cos, and so I get secant x tan x. That's its simpler version. And it's sort of nice, when you go to memorize these, the derivative of secant is secant tan. Not too complicated in its makeup there, okay? What was the last one I didn't do there? I did cosecant, secant. Oh, I still have cotan to go, so I'll go down here and do cotan. And the cotan one really plays out a lot like the tan one. So cotan of x, we're going to call cos x over sine x, and I'm going to use quotient rule here. Derivative of the top is negative sine x times the bottom, which is sine x, minus derivative of the bottom, which is cos x, times the top, which is cos x, all over sine squared x. A little more work here. I've got to common factor out this negative on the top, and I still get sine squared plus cos squared, which is so nice because that's the Pythagorean identity. Sine squared plus cos squared is 1. But I had to factor out the negative to get there this time, though, because it wasn't sine squared plus cos squared. It would have been negative sine squared minus cos squared, so I pulled the negative out front. And so what I get here, again, that's a legitimate derivative, negative 1 over sine squared x, but you're generally going to see it written as negative cosecant squared x, because that's slightly simpler there than the 1 over sine squared. Okay, so I really love these 4 derivatives because if you know the derivatives of sine and cos, which are reasonably easy to memorize, you can establish these other derivatives whenever you want to, but they're much faster to use once you have them memorized. So I encourage you to memorize those 4 as well as the 2 original ones. Those 6 are sort of the primary 6 that you should have available to you at all times. A couple examples to show how they're used. Determine the equation of the tangent to the graph f at x equals tan x over x at x equals 2. So now what I'm going to do is go take the derivative of this. I want the equation of the tangent, so I'm going to need the slope of the tangent at that value. And so tan x over x. So to do y prime, I go derivative of the top, which from above, the derivative of the top is secant squared x, times the bottom, which is just x, which I'm going to write out front. Just a little easier to write when you're writing trig ratios, write the anything you're multiplying by out front. It's just a little easier to understand. Let's see, minus the derivative of the bottom, which is 1, times the top, which is tan x, all over the bottom squared. And so what I get here is, I can't really do too much here. X secant squared x minus tan x all over x squared is what my derivative is. We maybe could tidy that up a little bit by multiplying through by cos squared. We'd get an x sine squared minus sine x cos x over cos x over x squared cos x, something like that. But I don't think it really achieves too much here in a final answer. But there you will see trig moves like that because we want to know what's the slope at a specific value. So why not just sub in here when x equals 2, y prime equals 2 secant squared 2 minus tan of 2 over 2 squared. Now this wasn't a nice one as far as, if it had been derivative at pi over 4 or pi over 6, pi over 3, pi over 2, something like that, then we could have easily got exact values. And you could carry this around as an exact value, I suppose. But generally speaking, once the exact value is this complicated, you'll probably see us go to decimals. You don't have to, but and you may want to keep it a certain example might say keep it exact. And so if you were going to keep it exact, what you'd keep is something like 1/2 secant squared 2 minus 1/4 tan 2, something like that. And then you'd carry that around as the slope. In this particular case, I'll go over to decimals. I'll show that as well. So I don't have a secant button on my calculator. So what I'm going to actually type in is 1 over cos squared 2 minus 1/4 tan 2. And so when I type that in, I'll just double check this. I go 1 divided by 2 times 1 divided by cos 2 want that squared, minus 1 divided by 4 times tan of 2. And when I do all of that, I get 3.43. I'm going to keep 2 decimal places, and that's my slope. So we have our slope of our tangent, y equals mx plus b, is going to be y equals 3.43x plus b. So now to get that b, I want to sub in an x and y pair. So I've got, from this 2, I got a point of 2 comma tan 2 over 2 is that point there. So the y value is tan 2 over 2 equals 3.43 times 2 plus b. And so when I take tan 2 over 2 and subtract 2 times 3.43, and just solving for b, I get negative 7.95. Again, to 2 decimal places. So the equation of the tangent is y equals 3.43x minus 7.95. And maybe I should put a little dot over all those to say I've rounded off there. Those are approximate answers. Okay. And again, I could carry around all those exact values, but it would be a big mess carrying around those exact values. Well, not the worst, but like I went to decimals here because those things were going to be complicated. Other applications, it says find the second derivative of y equals 7 secant x. So I'm going to first find the first derivative, and then I'll find the second derivative. Y prime equals 7. Okay, the derivative of secant x is secant tan. That's a nice derivative. I like the derivative of secant, me personally, because it's nice and easy to remember, no negatives or anything like that. But what we're stuck with here is a product rule when I go to do the second derivative. So I'm just going to underline that. That's going to be my first, and that's going to be my second. So when I go to do the double derivative, I go derivative of the first. The derivative of the first would be secant tan, and then multiply that by the second. Plus derivative of the second, derivative of tan, I'll look at my chart again, is secant squared. And you see how fast I did that. See, if you're always looking back at the chart because you don't have them memorized, things are going to take you forever. So sometimes in these things, you just stop and say, I'm going to take however much time it takes to memorize these things, and now my homework's going to go that much faster. Anyways, that was derivative of the second times the first. And so what I get as my double derivative here is 7 secant x tan squared x plus 7 secant cubed x. So I could switch over using common factoring and factor out a 7 secant x here. And so the first bracket would be tan squared, and the second bracket would be, or the second term, not bracket, would be secant squared. Now, and that could be enough there. You could keep it like that. But tan and secant are related. Let me just go over here and just do a little thinking about trig identities. Sine squared plus cos squared equals 1. And you can create a new identity, which you'll often see in things like trig toolboxes and so on, that relates secant and tan. And where it comes from is just dividing everything by cos squared. So I'm going to divide every term by cos squared x. So that's cos squared x over there. And so what I get is tan squared x plus 1 equals secant squared x. That's another identity. And it's not some crazy identity come from somewhere. It's just taking the Pythagorean identity and dividing it by cos squared. And so what I can get from that is I can get tan squared equals secant squared x minus 1. So that's pretty handy here because I can get this double derivative back to all secants if I wanted. So this is secant squared x minus 1 plus another secant squared x. So isn't that handy? Because what I end up with is y double prime equals 7 secant x times 2 secant squared x minus 1. So that's a little bit tidier version of it because it's only secants. I mean, sometimes it's worth it, sometimes it's not. Like if you want to find the double derivative of a certain value, then why would you go through all that? But if you want the most beautiful double derivative you can find, then that's definitely worth it. Okay, so that's the main 6. And we'll move along a little bit later. We'll start looking at inverse trig derivatives. But for now, that's a good start to really following up on how those main 6 derivatives work. Okay, have a great day.